we want to discuss all of the different Latin equations, all the linear equations, and how we can convert them into Greek and what they mean. So let's get the whiteboard set up. Okay, so there's my whiteboard, and let me just quickly reproduce this kind of table of all of the things that we learned before. Delta x equals v initial t plus 1/2 at squared, and v final equals v initial plus at. So you don't need to write all of this down again necessarily. I'm just getting it there so I can refer to it. You can, of course, download this later on the lecture notes on Blackboard. After we did kinematics, we had net force equals ma, and we found that work is F times delta x times cosine of theta, where we have kinetic energy being 1/2 mv squared, and we also talked about momentum, which is mass times velocity, and net force equals delta P over delta T. So this is basically the list I had before. I might have had them slightly reordered. But the idea, this is just to review that, these are the Latin versions, which are linear physics. And then we are going to convert them into Greek versions, which are the rotational versions of the equations. And that looks like instead of a delta x, we have a delta theta. Instead of a v initial, we have omega initial times time plus 1/2. Instead of at squared, it's alpha t squared. And we can do the same thing for all of our kinematic equations, just translating the symbols into Greek. And there's basically a perfect correlation between these three kinematic equations and these three rotational kinematic equations. Then we can talk about net torque. And we focused on when there is no alpha, when the thing is not rotationally accelerating. Today, we can talk a little bit more about what happens when it does accelerate. We'll have to understand what this thing what this I is, moment of inertia. And we have rotational work, which would be the torque times delta theta. And we have rotational kinetic energy, which is 1/2. Instead of m, it's I, and instead of v, it's omega. But it's the same kind of thing. Our angular version of momentum uses the letter L, and it's equal to angular mass times angular velocity, or moment of inertia times omega. And last but not least, we would say net torque equals the rate of change of the angular momentum. Okay, so that's our complete translation. Today, we're going to focus mostly on these guys, but additionally, we are going to single out this moment of inertia and talk about it a little bit and try to get an understanding of what it is. And then once we have that understanding, you will be able to do the lab that is assigned for Monday. This lab is a little different from the other labs because it's not a computer simulation. You're actually going to physically get stuff, get objects in your house and do a lab. So we'll talk about that toward the end. So that's an overview. Now, in order for us to kind of proceed to talk about the kinematics, I want to remind you just what all of these things are. So delta theta, you know, this is pretty self-explanatory. Change in theta, in the angle or the orientation. Omega is defined as the rate of change of the angle. So it's going to have units of radians per second. And alpha is the rate of change of omega. So it's got radians per second, or radians per second squared. So those units where theta is in radians, those units are kind of our keys when we're reading problems and trying to translate them, trying to interpret them, to knowing what we're talking about. So the theta is kind of like our x variable, our displacement, and the omega is our velocity variable, and the alpha is our acceleration variable. So a sample problem could say something like the following. A wheel starts at rest and begins rolling with an angular acceleration of 2 radians per second squared. So we would, if we were to translate that, we would say omega initial equals 0 and alpha equals 2 radians per second squared. So a wheel starts at rest and accelerates at a rate of 2 radians per second squared until its angular speed is 50 radians per second. So that would be omega final equals 50 radians per second. And we want to know how many times did the wheel spin. Okay, so number of rotations equals question mark, and that would basically be delta theta. That's what we're looking for. So then we go back to our kinematic equations and we say, you know, the same process we would have done before if we had V initial, A, you know, V final, and delta X. If we knew those things were what is presented in the problem, we would go to our master equations and we would want to pick this third master equation. But since we're using rotational variables, we pick the third rotational equation. So we have omega final squared equals omega initial squared plus 2 alpha delta theta. And we know that omega initial is 0, so we can cross that out. We know omega final and alpha and 2, so we can solve for delta theta. It's going to be omega final squared over 2 alpha, and that would be 50 squared over 2 times 2. So that's 500 over 4. I think that's 625 radians. Now, the units have to be radians. All of our master equations relied on saying, you know, delta x equals r times delta theta, or v equals r times omega, or a equals r times alpha. All of these are only true for radians, okay, because they come from the definition of arc length. So even though the problem wants to know number of rotations, what we got was the number of radians. So at the end, we have to convert radians to rotation. So 2 pi radians would be 1 complete rotation. So a rotation is 360 degrees. And so then when we want to know the number of rotations total, we have to divide by 2 pi, and we get 99.5 rotations. Okay, any questions about that example? Okay, now sometimes the problems will want us to connect the rotational motion with linear motion. So of course, if this is a wheel, you know, and it's rolling down down a ramp, and we want to know, you know, for example, what is the distance that it traveled, and we want to know what is its final velocity. Well, that's where these equations in the box here come in, because those are the keys to translating back from Greek into Latin. So for example, in order to do that, I'll need to know the radius of the wheel. You know, if the radius is, let's say, 20 centimeters, and we want to find delta x and v final, then we would just use these relationships. Delta x, so that's how far did it go when it was rolling, would be equal to 0.2 meters times 99.5 radians. Now, units kind of look funny because it looks like we're going to get meter radians. So this gives me 19.9 meter radians, it looks like. But we don't really include the radians. Why is that? Well, this equation, delta x equals r delta theta, in the first place, it has meters for delta x, and it has meters for r, and then we have radians. So the radian, it's not a real unit like a meter. It's not like a radian somewhere. A radian is defined as a ratio of a circumference over a radius. So or an arc length over a radius. So technically a radian is no unit at all. We just write the radians to remind ourselves that we're allowed to use these equations. Okay? So when you're going from rotational, I don't want, those are rotations. I want to use the radians. 625. That should have been 625 radians. I'm going on about radians, but I didn't use the radians. So the actual answer is 0.2 times 625, and that is 125 meters. Okay, so, but back to this point. That mistake exactly illustrates it. I should not be using rotations. I have to use radians if I'm going to use these translations between Latin and Greek. I have to be in radians because they're designed for that. And the radian is the marker that reminds me I'm allowed to do this. But other than that, we just have to drop the radians if we're going from Greek into Latin, or that is rotational into linear quantities. And we have to just add radians if we're going from linear quantities into rotational quantities. So once we find delta x, we can find v final the same way. V final is going to be r times omega final. So that's 0.2 meters times 50 radians per second. So that's going to be 10. It looks like meter radians per second, but we just drop those radians. Okay, so that allows us, that's how we connect rotational motion with linear motion. Now, typically, when we do that, there has to be some fine print in the problem. This is very similar to how a spring problem would say it's a massless spring, or you know, when we're doing, I don't know, torque with a ladder on a wall, we say it's a frictionless wall, or you know, those types of approximations. Ignore air resistance. We would have to say that this is only true if we have rolling without slipping. Okay, so that's the kind of key word you'll see in problems in the textbook that tell you that these box equations are valid. Because after all, it's possible that something is spinning, like a tire on a car could be spinning without the car going anywhere. That's going to happen, for example, if there's no friction. Or you guys all know that trick you do with the hula hoop, where you take a hula hoop and you throw it and you spin it, and it sort of skids along the ground for a while, but eventually it kind of catches and then it rolls back to you. Raise your hand if you know what I'm talking about. Okay. So that would be a case where, you know, that hula hoop is slipping. It's rolling, but it's slipping until it sort of catches onto the ground and it gets enough friction so that it can't just spin in place, but it has to start rolling back to you. Once it starts rolling back to you, that would be then rolling without slipping, and that would mean every time it goes through a complete, you know, revolution, that it has to travel a certain distance equal to its circumference. So anyway, we're not gonna have any problems that have rolling with slipping, but you're going to be kind of looking for that keyword, and that's typically going to mean, or key phrase, that we're justified in relating the linear and the rotational equations. Okay, any questions? Okay, so let's try one from the textbook. Let's see. Looking in the wrong book. Okay, this is the 3000 Problems book, and the problem number is 11.14. So we're just going to practice reading and translating and then solving. A phonograph turntable rotating at 8.16 radians per second slows uniformly to a stop in 6 revolutions. So first of all, it's rotating at 8.16 radians per second. So when I see those units, radians per second, I have to know that is an omega. So I have omega equals 8.16 radians per second. I don't know which omega it is. Is it omega initial or omega final? Well, it's doing that, and then it slows to a stop, so this must be the initial. And when it slows to a stop, that tells me omega final equals 0. And it does this in 6 revolutions. So I have to know what kind of thing is a revolution. A revolution would be a delta theta. But I don't want my delta theta to be expressed in terms of revolutions. So I have to convert. 1 revolution is the same as 2 pi radians. So this would be 12 pi radians. So I want to convert anything that's not in radians to radians as fast as possible. Find the angular acceleration in radians per second squared. So alpha equals question mark. Okay, so there's my translation. Once I translate, it is almost a no-brainer to go in, look at my equations, and to recognize that since I don't have time, I don't want to use the first or second equations. I would rather use the third equation. However, you could use the first and second equations, but just would be harder. So omega final squared equals omega initial squared plus 2 alpha delta theta. My omega final is 0, so I can cross that out. And maybe move the omega initial squared to the other side. And then we divide both sides by 2 and by delta theta. So minus omega initial squared over 2 delta theta equals alpha. My alpha would then minus 8.16 squared over 2 times 12 pi. I get negative 0.88, and my units must be radians per second squared instead of meters per second squared. When we have a rotational or angular acceleration, it's going to be radians per second squared. You can see how that works by looking at what we have. We have radians per second quantity squared over something with radians. So that's radians squared per second squared over radians, and one of those radians cancels out and leaves me with radians per second squared. Okay, any questions? Okay, so raise your hand if you can see how this is very similar to what we did at the very beginning of the class, our regular kinematic equations. Okay, good. So you can think of this as maybe a little review in a way of that stuff. It just reinforces what you already learned. Think of this as almost a freebie. You're going to love these problems. When you get these in the contest, you're never going to cross these out because these are so similar to what you have already learned. But let's do another one for a little more practice. This one is also 3,000 problems, number 11.16. Okay, in seconds, a car, so I'm just going to start right there, t equals 7 seconds. A car accelerates uniformly from rest to such a speed that its wheels are turning at a rate of 6 revolutions per second. So it says from rest, and that means omega initial equals 0, to such a speed that its wheels are turning at a rate of 6 revolutions per second. So that means omega final equals 6 revolutions per second. Again, I don't want revolutions, I want radians. So I'm going to immediately get rid of the revolutions, and we have 12 radians per second. Don't forget the pi. It's easy to forget the pi. 12 pi radians per second. What is the angular acceleration of the wheel? So alpha equals question mark. Through how many revolutions does the wheel turn? That would be asking me for delta theta, but asking me to go back to revolutions. Okay, so looking at what we have, time, initial, omega final, and alpha. That looks perfect for our second of the 3 rotational master equations. So we're going to have omega final equals omega initial plus alpha t. And we can cross out omega initial. And alpha is just omega final over t. So that's 12 pi radians per second over 7 seconds. That gives me 5.39 radians per second squared. And when I did that, I had to make sure that I multiplied by pi. If you just do 12 over 7, you get like 1 point something. Okay, you have to multiply by pi, either using the pi button on your calculator or just 3.14. So once I have alpha, I can find delta theta. Let's go ahead and pick the first equation. Delta theta equals omega initial t plus 1/2 alpha t squared, where again we can cross out the first term, the omega initial is 0. And we're going to get 1/2 times 5.39 times 7 squared. That's 131.9 radians. But the problem asks us through how many rotations it makes. If we see rotations or revolutions, those mean the same thing. So revolutions, it says how many revolutions. You know that one revolution is 2 pi radians. So I can cancel my radians out to get back to revolutions. And we get 21 revolutions. Okay, any questions? All right, so I want to leave it kind of for you. I don't want to go too far into this, especially when you have a contest coming. But you know, once you have the contest, you actually do have some homework planned for the weekend on this stuff. So you know, take the contest, go drinking to sort of drown your sorrows, or you know, orange juice, drink some orange juice to rehydrate. Maybe not, maybe just water. Drink some water. And on Saturday, do some problems like this. I think you're going to find they're refreshing, they're easy, it's like a little break. So I want to talk again about some of the rest of these equations, and I want to focus on this thing called I. Okay, the thing called I. So we have net torque equals I times alpha, and that is like our net force equals ma equation. So what I is, it would be the net torque divided by the observed angular acceleration. In terms of units, remember a torque is a Newton times a meter, and an angular acceleration is a radian per second squared. So if we kind of try to assess these units, keeping in mind what a Newton is. Newton is a kilogram meter per second squared, and we divide by radians per second squared. The second squared parts just cancel out, and we get kilograms times meters squared, and the radians, we don't really need them. Okay, so the first thing we can notice about this moment of inertia is it's related to mass, but it's also related to maybe the area of the object. So let's just do kind of a thought experiment. I normally do this as a real experiment in class, but if we had a meter stick and we want to make it rotate, so we, you know, maybe hold it, you know, your thumb goes here and your fingers kind of curl over. How many fingers do you have? There we go. So you're holding this and you want to make it rotate back and forth. Just kind of, you know, like this, swinging it back and forth. You will feel some resistance. So this is where normally in class pass that around. you can try this at home with any kind of like just a broom handle or something, some kind of stick. Just wiggle it back and forth. And you'll feel resistance, usually when you get to the end, when you get kind of your wrist is twisted and you're stopping it and trying to get it to rotate in the other direction, that's when you're applying an angular acceleration. You feel this resistance. And the resistance has to do with several factors. One thing it has to do with is the mass. So if you do this with a steel meter stick versus a wooden meter stick, you'll feel a real difference, okay, even though the sizes are the same. So we know that this depends on the mass, okay? But if we had a 2-meter stick that had the same mass, and we try to rotate this, we would discover that the 2-meter stick was harder than a 1-meter stick, even if their masses are the same. So it depends on, in a way, the size of the object. So let's say you have a 1 kilogram meter stick and a 1 kilogram stone. And you hold the stone in your hand. If you can see my little, those of you online can't really, like, watching the video can't see this. Let me just take off the whiteboard for a second. So if I'm just holding a stone in my fist and I just shake it back and forth, there's some resistance, okay, to rotating that, but not nearly as much as if I have a meter stick extending at a long distance. In a way, this is because, when I spin the meter stick, the ends of the meter stick have to move really fast. And when the ends of the meter stick are moving really fast, they have a lot of kinetic energy, and that means it costs me more energy to get spinning than it would for a stone or just a small mass in my hand. So the weight, the size, but also the distribution of the mass has an impact, and we could illustrate that by just holding the meter stick on the end. Okay, if we instead have a meter stick like this, and again, I encourage you to try this with, a broom handle or something, some kind of stick at home, but you just kind of, I don't know what I'm doing here with my drawing, but anyway, you hold it on the end. I guess you would want to hold it with your thumb on the other side. And then you spin it back and forth, almost like you're swinging a sword, but around your wrist. You'll see that this is much harder. Even though it's the same meter stick or same broom handle, it has the same length, it has the same mass. So the mass and the size are the same, but the distribution of the mass, meaning where the mass is located relative to the axis of rotation. Okay, so the moment of inertia, this thing, it is more complicated than simply knowing the mass of the object. We talked about opening a door as our example of applying a torque. And we said, what are the things that influence, how hard it is, easy or hard it is to open the door, the things about how I push. And the things about how I push were how hard I push, where I push, what angle I push. But people in the audience here in the class also mentioned some other things that do influence the difficulty. And those are things that have to do with the door. How heavy is the door? How big is the door? What's the door made out of? So those are all factors in this thing, the moment of inertia. So we are generally not going to be able to compute the moment of inertia for a particular object, but instead we look in a table. So these calculations have been done already, and the moment of inertia for a rod about the center, meaning if we rotate it about the center, that's my picture in the middle here of the meter stick, the formula for that is 1/12 times the mass times the length squared. So it's got something having to do with the mass and with units of kilograms, and something having to do with the size with units of meters squared. And then there's a constant which is just based on, so constant based on the geometry. That is how it's shaped, how far away the mass, the masses, individual sort of molecules, how far they are from the axis of rotation and so forth. If we have a rod about the edge, the formula would be 1/3 ml squared. So that difference between 1/12 and 1/3, that's a factor of 4, meaning it's 4 times harder to rotate the rod from the edge compared to the middle, and that's all because of the geometry, the way the mass is distributed relative to your hand. And I'll give you a few others, but there's a table in the beginning of one of the chapters in these 2 books. One of the 2 chapters on this kind of stuff has a table. And the PDF textbook also has a table. But for a solid sphere, the formula is 2/5 mass times the radius squared. For a hollow sphere, it is 2/3 the mass times the radius squared. For a disk or a cylinder, it's 1/2 the mass times the radius squared. For a ring, like a hula hoop, it's just m times the radius squared. So hopefully you can see a pattern here. The pattern is moment of inertia is always equal to some constant times the mass times either the length or radius squared, to something about the size of the object. It always looks something like this. And that constant is geometric. It has to do with the shape. If it's a solid sphere, that constant is 2/5. If the sphere is hollow, it's 2/3. If it's a disk, it's 1/2. It's a ring, it's 1. There's sort of a 1 hiding in there. And really, what determines the constant is the constant gets bigger the more the mass is concentrated at a far radius. So if you think about a ring, like a hula hoop, and it's going to be rolling, down a hill or something, all of the mass is at the maximum radius, all of it. And if all of the mass is at maximum radius, that's when you get a 1. And in other cases, you get generally something less than 1. So for a disk, or let's say it's a cylinder, so you can think like a can, a can of soup or something, but a solid can of soup. So frozen. If you freeze a can of soup, then it makes a cylinder. And that has a lot of mass at the maximum radius, but it also has mass at more interior radii. So it's got mass going all throughout, but it has a substantial amount of mass at the edge and a substantial amount in the center. And so that kind of averages out to a 1/2. If we have a hollow sphere, it's a sphere and it's hollow, the mass is largely at the edge because the inside is empty. But there's some mass that as it rotates, kind of in this vicinity, that mass is close to the axis of rotation, so it doesn't contribute much to the sort of difficulty of rotating. That gives you a constant that's close to 1, but a little less. And for a solid sphere, that's kind of like you have a cylinder and you cut away some of the stuff at the corners, kind of up here and up here. You're cutting away some of the mass that's more toward the edge, and so this kind of goes from 1/2 down to 2/5. At any rate, I know that there's no way for us without knowing in detail how to calculate this to know why the numbers are what they are. But conceptually, just think to yourself, the more the mass is spread out to a larger radius, the bigger this constant is going to be. And the more the mass is compact and located toward the center, the smaller the constant will be. Okay, but for purposes of solving problems, these constants are usually either given or we look them up in the table. Okay, any questions? Okay, so what we're going to do, I'm just going to talk to you briefly about the lab exercise. And this lab exercise, we're not going to know what we should expect as the outcome until next class, because I don't want to go too deeply when you're preparing for a contest into new theory, and this is kind of a complicated thing. But because objects, when they're rotating, they get kinetic energy, and the kinetic energy equal to 1/2 I times omega squared. Objects with different moments of inertia, if they roll down a ramp, so let's just imagine we have some objects. Maybe we have a ring, like it could be a hula hoop. It could be a can of soup that's empty and you cut the top and bottom faces off, so it's kind of like a hollow cylinder with no side faces. If we roll that down a ramp, as it rolls, that potential energy that it starts with is converted into both translational and rotational kinetic energy. And if we do the same thing with a cylinder, then that cylinder is going to have the same transformation from potential energy into kinetic energy, but it's going to transfer differently because the moment of inertia is different. So that is, if we have a race between different objects with different geometries, they will not have a tie. They will have different speeds. So this would be a cylinder, a solid cylinder. Or we could have a solid sphere. Or we could have a hollow sphere. And have a race between all of these guys. And that's what you're going to be doing in your lab. Now, you'll have a whole document that gives you detailed instructions. But the idea is you're going to be holding races between objects. And you'll have to kind of rummage around your household to find appropriate objects. So kind of be thinking in advance, what can you use as a ring? Like I said, something like a hula hoop is good, but a hula hoop will fall over if you're not careful. So something like a used can of, something with the top and bottom cut off with a can opener would work as a ring that would be kind of stable. On the other hand, a cylinder, I'm sure you can find some cylindrical objects, but if you can't, just take a can of stuff and freeze it so that the liquid inside is not sloshing around as it rolls, but is solid. And then you have yourself a nice solid cylinder. A solid sphere could be orange, or maybe if you have a ball of some sort that is solid, like, I don't know, some balls are solid like a lacrosse ball or field hockey ball, something like that, versus a hollow ball, which, a basketball or soccer ball or something would count as a hollow sphere. A baseball would be a solid sphere. So you're going to have to rummage around your house, be creative, find objects, and you'll have a series of races to run. And what you'll want to do is you'll want to take video footage of these races. And I'll go ahead and show you just an example before we go, and just to give you an idea. Give me a second here. Okay, so hopefully you can see this. This is just an example someone did last semester. This student took, she had a yardstick. She had a few objects that she placed kind of in front of the yardstick so she could then remove it really rapidly and they would be starting from rest. And then she took, I think with her phone, she just took a high frame rate, so slow motion video, so that you could see kind of in detail who wins the race and so forth. What's first, second, third, and fourth place in kind of a photo. So you'll have some exercises like that in the, explained in the document. And any questions? Does that make sense? Okay, so so that's it for today. Get yourself prepared for the contest. I'm already set up to meet with a number of students later this afternoon. If you need some help now, you can stick around. You can also set up a time later to meet if you're not ready to meet yet, or maybe you don't need to meet with me. But I'll end the recording now, and after you prepare for that contest, go ahead and take a little break, but then you do have homework for the weekend, including this sort of different kind of lab experiment. Any questions before we sign off? Okay.